For the second part of motion of several particles, we have absolute dependent motion analysis of two particles. So this is actually for the pulley system. So in some types of problems, the motion of one particle will depend on the corresponding motion of another particle. So this dependency commonly occurs if the particles, here represented by blocks, are interconnected by inextensible cords which are wrapped around pulleys. So we have an figure here below. So from this example, the movement of block A downward along the inclined plane shown in this figure will cause a corresponding movement of block B up the other incline. So if ever the block A is moving downward, so the movement of block B here will go upward. And we can show this mathematically by first specifying the location of the blocks using position coordinates SA and SB. So we note that each of the coordinate axis is, first, we measured from the fixed point or fixed datum line, and second, measured along each inclined plane in the direction of motion of each block. And the third one is has a positive sense from C to A and D to B. So if the total chord length is LT, that is connected from A to from block A to block B, the two position coordinates are related by the equation SA plus LCD plus SB is equal to LT. So the total chord length here, based on this example, is equal this SA plus the chord length here in the arc passing in passing over arc CD, and also plus the length SB. So here LCD is the length of the chord passing over arc CD. So taking the time derivative of this expression, realizing that LCD and LT remain constant while SA and SB measure the segments of the chord that change in length, we have this equation. So that is, we differentiate the position with respect to time, and it becomes the velocity. So the negative sign indicates that when block A has a velocity downward in the direction of positive SA, it will cause a corresponding upward velocity of block B, while if the B moves in the negative, which is B is, or block B moves in the negative SB direction. So in a similar manner, if we determine the time differentiation of the velocities, that yields the relation between the acceleration. So that is, the acceleration of block B is equal to negative acceleration of block A. So what happens here, why we consider the position of block A and block B, if we withdraw again the two blocks, this is block A, block B. So take note, this is SA, SB. So if block A is moving downward, therefore block B is going upward. So what happens? The length of block A will get longer, and the length for SB will get shorter. So here our SA is um, getting longer as block A is going downward, and SB is getting shorter when block B is going upward. So that's why there is a change in length for the um, chord length for SA and SB. A more complicated example is shown in the figure below, which is this one. Um, in this case, the position of block A is specified by SA, and the position of the end of the cord from which block B is suspended is defined by SB. So here, SB defines the position of block B, and SA defines the um, position for block A. So as shown, we have chosen position coordinates which have their origin at fixed points or datums. So for SB, its datum is here. It is um, above the block B, and for block A, its datum or fixed point is to the left of block A. And second, are measured in the direction of motion of each block. And the third one are positive to the right for SA and positive downward for SB. So during the motion, the length of the red colored segments of the cord remains constant. And if L represents the total length of cord minus these segments, then the position of coordinates can be related by the equation. So we have 2SB, which is this, 2 lengths, that is 2SB, plus H, which is this one, plus SA, and that is equal to the total cord length minus the red colored segments that remains constant. So since L and H are constant during the motion, the two-time derivative yields the following, that is 2VB is equal to negative VA, and for the acceleration that would be 2AB is equal to negative um, acceleration of block A. Hence, when B moves downward, A moves to the left with twice the motion. So that's why for the absolute dependent motion analysis of two particles, it is very common to pulley system because the movement of one block is dependent to the other block. So for the procedure for analysis, the previous methods of relating the dependent motion of one particle to that of another can be performed using algebraic scalars or position coordinates, provided each particle moves along a rectilinear path. So when this is the case, only the magnitudes of the velocity and acceleration of the particles will change, not their line of direction. So the first thing, you establish the position coordinate equation. So you establish each position coordinate with an origin located at the fixed point or datum. It is necessary that the origin be the same for each of the coordinates. However, it is important that each coordinate axis selected be directed along the path of motion of the particle. And using geometry or trigonometry, relate the position coordinates to the total length of the chord, which is LT, or to that portion of chord L, which excludes the segments that do not change length as the particles move, such as arc segments wrapped over pulleys. And if a problem involves a system of two or more cords wrapped around pulleys, then the position of a point on one chord must be related to the position of a point on another chord using the above procedure. So we have actually two example problems for this one if it involves a system of two or more chords wrapped around pulleys. Then separate equations are written for a fixed length of each chord of the system, and the positions of the two particles are then related by these equations. And after you establish the position coordinate equation, you apply time derivatives. So two successive time derivatives of the position coordinate equations yield the required velocity and acceleration equations which relate the motion of the particles, and the signs of the terms in these equations will be consistent with those that specify the positive and negative sense of the position coordinates. So we will have three example problems for this topic. The first one is involves only a system of it involves only one chord that wrap around pulleys, but for the other two examples, which is example 2, example 3, are problems involves a system of two chords wrap around pulleys.